Welcome back to yet another episode. Today we will focus on new components and how to use them. To begin, what's one component you see almost everywhere? From your house to your school, from your car to your microwave. And it can either start or stop programs and circuits. That's right, it's a switch. And similar to a switch, today's component is a push button. For this circuit, we will need a push button, an LED, 2 resistors and 6 jumper wires. Now for this circuit, we want a connection between the power rail and the 5V pin. But wait, why do some components need a voltage pin, where others like LEDs don't? The difference is in its purpose. An LED is a passive output, where if current is applied to it, it will turn on, end of story. But on the flip side, the push button is an input device. It detects highs and lows, ons and offs, and it needs 5V to provide a clear signal. Now, if you've seen the previous video, you may have noticed that we use the HCSR04. We use the VCC pin and the ground pin for it. Well, why does it use both? The catch here is that it is an active sensor, aka an input device, and it works a little differently. It needs a 5V pin to give clear signals, but also uses a ground pin current for its internal circuitry. Now back to the circuit. We insert the button like this and make a connection between one connected row to the power rail and a connection to the Arduino pins. A cool thing about the push down button is that all 4 of its legs are electrically connected. If we leave it like this, the button will have a high signal, as it's only connected to the 5V. We fix this by adding a connection to the ground pin. But wait a moment, didn't I just say that the push button only uses a 5V pin and is not an active input device? The twist here is the pull down method, where we use not a jumper wire to make the connection but a resistor, therefore pulling the current from the ground pin to 0. So the button has access to both voltages, so it can now have a high and a low signal. If we didn't use this resistor, we would have damaged the component. But it doesn't stop there. We have to program it now. We will begin by making our constants for the LEDs and the buttons. Then make sure to introduce the constants in the setup function, but the button must be an input. Now we use a new command called digital read to detect values of variables. Now we use a new command called digital read to detect values of variables. So we use an if statement now to say that if the button is high, then turn the button on. So we write it this way so that it will check the value of the variable and say, is it equal to high? If so, then we continue with the code. If not, then skip the if statement and go to the else statement where we say else turn the LED off. Let's test it out now. Nice. You can view its effects on the serial monitor and the plotter as shown. Now our second component is the key to being able to change and control components and circuits. From music to industrial systems, it's a potentiometer. For the circuit, we will need a potentiometer and 4 jumper wires. Connected as shown. It has 3 pins, one for voltage as it is an input component, one for ground pin, and the middle one for its own pin. We won't connect it to a digital pin as it only reads high and low values. Rather, we will use an analog pin to read various values. Now to open the sketch, we won't have to introduce a potentiometer as an input like a digital pin. But instead, we will have to write serial begin 9600 to use all serial tools. Now in the loop function, we make a variable called sensor value and make it equal to the value of the potentiometer. This can be measured by stating analog read command and the analog pin used. Finally, write serial pin ln and sensor value, and then add a small delay. Let's test it out now. When you twist the potentiometer, you will notice the values range between 0 to 1023. Why? The Arduino has a ADC, or an analog to digital converter, which converts the changing voltage to a number the computer can work with. And it just so happens to be in this range, as it is a 10-bit binary number. Now you know what would be fun? Seeing the voltage values change as we turn the potentiometer. But how would we do that? We should go back to the sketch and do some calculations. Below our first variable, we create a float variable called voltage, and we make it equal to the equation sensor value multiplied by, in brackets, 5 divided by 1023. This is a float variable because it can work with decimals unlike integers. And we make sure it's shown on the serial monitor as shown and test it out. This is a little boring. How about we take it up a notch? Let's use our new skills to control the brightness of an LED. For this, we will need the same circuit but an additional resistor and a LED. Our first big problem here is that the analog read command takes values from 0 to 1023, but the analog write command takes an 8-bit binary number, meaning 0 to 255. Well, there's a simple solution. On our sketch, we create an integer value and make it equal to our sensor value and divide it by 4. Why? Because this now makes a new range, 0 to 255.75. But the magic here is that because a variable is an integer, the 0.75 is ignored, thus solving our problems. Next, we will use an analog write command and mention our digital pin used, and instead of saying high or low, we will put in our integer variable so that the LED brightness will be equivalent to the converted value read from our potentiometer. There's only one more thing left to cover in this video, and that's the map command. It's a more convenient way to convert values. To start, delete this line here. Now state our variable, then the map command, and state the variable which value you want to change, and then write the original minimum and maximum values followed by the minimum and maximum values you want. That will be all for today, and in the next episode we will take our skills learned to create a second major project. But until then, take care.